The Sabir project is a co-design initiative fostering the network of NAICS from the Mediterranean. The project, led by the OASI Center Italy, was named Sabir as the Mediterranean lingua franca. This was a language that was used in the Mediterranean basin from the 11th to the 19th century. Our goal was to exchange best practices and enhance the outcome of previous experiences and projects that were led, that included actually NAICS from the Mediterranean countries. The outcome of this project are multilingual published activities that were designed for high school students in a spirit of an inquiry-based learning or IBL approach. But let's start from the beginning. So the co-design is a pillar of the approach that is used by the Italian Office of Astronomy for Education. Co-design was in fact largely exploited as the method of several previous projects led by the same center, in particular Mirto, STEAM-Med, and within last year also Fresco, that will be presented in the evaluation session. Since the OAI Center Italy is located in the Mediterranean area, the idea was to build a community of Mediterranean actors within this approach. The Mediterranean co-design approach has different aspects that are listed here. So it fosters a person-centered learning, fosters also the collaboration between peers, between NAICS. It has a strong interculturality aspect, and astronomy here is also used as a tool for learning, also social skills, and it enhances previous experiences. One of the main outcomes of the Sabir project, as I said, is to deliver IBL-like activities for the final target of high school students. The particular emphasis here is to promote and encourage innovative, open, and critical learning. Within these overall goals, we want also to emphasize the social aspect that is related to the strengthening of a community around in the Mediterranean area, around the Mediterranean NAICS, enhancing best practices and also implementing the MET co-design process. At the start of the Sabir project, our first step was to build a common ground. So we were asking ourselves, what is an IBL activity in this context? An activity that is inquiry-based and generally contains a number of specific parts that goes from orientation, conceptualization, investigation, and conclusions, and those parts are related among each other. Frequently, the need of discussion and reflection among students leads to a deeper understanding of the initial problem that wants to be addressed in the activity. Now, the first thing that we noticed is that preparing an educational activity, a common bias, is that we focus on the content area, so enhancing the investigation area of this graph. And this was, in fact, our case. We made an initial survey among the participants, finding that not only the content area was prevalent, but also that some of the connections between different areas were missing or underrepresented. Therefore, after we settled the common ground, the participants to the Sabir project were asked to focus on the skills area. And in particular, this could also lead to a more scientific approach in the learning. Also, they agreed on enhancing the discussion among students. So to reach this goal, we tried to answer two general questions: how to engage the students and how to create the conditions for the students to discuss and openly express themselves. The project itself developed in the following way. We started with a first meeting in February where we needed to present the general aspect of the project. And in the second meeting in March, we started from the same grounds, especially with what our activities would look like, and we were brainstorming about possible ideas and projects. The online part, that is basically the red and the gray part of the co-design process, was the basically the gray part was the co-design process that was at work, since participants presented the initial structures of the activities and were given the opportunity to co-design each other's activity. The last part of the project was realized as an in-person residency in Milan, in Italy. And the final phase, so the residency in Milan, was in the beginning of September and was really very intense. Each of the participants co-designed the final stages of their project, and the co-design was happening in pairs with one facilitator, and overall there was one of us that was in charge of the evaluation of the process. The activities that we chose were different. Two of them, the first two, asteroid mining and exploring exoplanets, were proposed as mostly new activities, while the other two, about water rockets and the place in our universe, were two activities that were already developed and tested, but in a non-IBL context or not completely IBL context. Initial activities were developed also with the help of other NAICs from the same countries that are listed here. All the activities were and will be submitted to Astro-IAU editorial board, and the activities that were already published are here in orange. Each of the activity will be translated after publication into different languages: Arabic, French, Spanish, Turkish, Slovenian, and Italian. So I should also say something about the evaluation. So the evaluation of this project is happening in two different ways. So it will be done on the process and on the activities. So looking at the co-design process, our goal is to evaluate how the, let's say, translation of activities into IBL-like activities had an impact on the community of Mediterranean NAICs. The other aspect that will be evaluated are the activities themselves. We want to understand if the activities were in fact developed as inquiry ones, so are compliant within the IBL structure, or how relevant the inquiry is when activities are done in different countries. What we learned from this project is that the co-design is not straightforward. It can be very slow, especially the online part could be very, very slow. The discussion in pairs during the residency was in fact very efficient, and also it was facilitated by the fact that the NAICs knew each other. The activities were tried to be developed from content-oriented to skills-oriented, and the building of a community, as I said, has a very positive impact on the project. The evaluation of the activities will be done also by testing the activities in schools with questionnaires or with interviews, and during the evaluation there will be time also to write the teacher's guide and the student's guide. And if anyone wants to participate to evaluation or help us with the translation, we will be very thankful to them. So thanks also to all the people involved. So Aishagul, Naira, Jean-Pierre and Hassan, and all the others that helped in the developing of this project. Thank you.
My name is Chris Impey. I'm a distinguished professor at the University of Arizona, and I want to talk about tools and tips for teaching astrobiology. Astrobiology is a subject enjoying strong and healthy growth. Here are some numbers that indicate that growth. At the professional level, in attendance at the AbSciCon meetings every couple of years, in the number of AstroPH preprints with astrobiology as a keyword, and in the number of papers on astrobiology in the astrophysical and astronomical journals. As an indication of more popular interest in astrobiology, you can also see strong growth in Google Trends in the number of searches the general public make on the word astrobiology. This is a stronger growth than we would see for analogous statistics for the whole field of astronomy. Astrobiology is experiencing strong growth in large part because of the exponential rate of exoplanet detection. You can see it here illustrated over the 35 years since we've been finding exoplanets. This exponential rate of detection is extraordinary in any scientific field. In fact, it mirrors something that is associated with our technology, which is the improvement in the quality and capability of cell phones. So that's a striking indication of how central astrobiology is at the cutting edge of research these days. When it comes to teaching astrobiology, we're in a situation where things haven't changed as much as they should. Most college classes are still taught in a traditional transmissive way in a classroom, even though the efficacy of classroom teaching and lecturing has been demonstrated to be relatively poor. There's foundational research, including this famous paper by Scott Freeman in 2014, that shows that active learning methods, broadly defined, are just much better at inducing student learning. So here we have data across a number of fields of science, across many classes all over the country, showing improvement in scores of students in science classes for non-science majors, and decrease in the failure rate, independent of instructor. So active learning clearly works, and we should all be trying to introduce it in our astrobiology teaching. In my case, I've taken classes of size 100 to 150 people and reduced the amount of lecturing to less than 50%. Because 1 of the 2 days a week we do labs or activities where students broke into small groups of 3 or 4 with a joint grade. This helps with social learning, and even the lectures are broken up by discussions and debates and classroom demonstrations. I've managed to work the course so that there are no multiple choice or objective tests, just occasional quizzes to spur attendance and to get students reading. This instructional model works well in large classes with only one TA and the help of undergraduate teaching assistants or preceptors. I also use a portfolio method in some of my teaching of astrobiology. And this is where students over a semester build a portfolio of their work, where they look at journal articles in astrobiology, not technical but maybe popular ones, or in the news media, and they analyze them and they judge this information. They also read interviews with astrobiologists and dissect them and understand and get a personal insight in what it means to do astrobiology. They do citizen science work as well. And then at the end of the semester, they do an out-of-the-box project where they can take their own skills in other areas. They can make the project art or music, video, whatever they want. It's a very flexible framing of an astrobiology topic, and students really get into that. Students are also able to improve their grade by iterative grading on the assignments, where they submit a draft and then get a final grade for a second submission. We also want to have a situation where you can do demos that illustrate famous astrobiology topics. There's a classic one that involves extracting DNA visibly in the classroom using either strawberries or kiwi fruit, which happen to have very large cells with soft cell walls. The other ingredients you need are fairly simple to obtain: cheesecloth, salt, shampoo, and rubbing alcohol. And you can see the instructions here. What happens is, at the end, you're able to extract with a toothpick strands of DNA, not single strands of DNA, but clumpy DNA from the boundary layer between the alcohol and the other solution. And it's a quite striking demonstration. Students really enjoy it. I also do an activity that has variations which apply in physics and in other fields, but in the astrobiology version is mystery boxes. So we have 4 mystery boxes, and you can scale up the numbers of these to serve large numbers of students. And the mystery boxes have no holes, they're sealed, and they can only be inspected by smell, sound, or the feel, or the way they sound when they're shaken. They're unlabeled, of course, and one has an inert non-living content, sand or small grains of gravel. Another is a formerly living object, such as peanuts. A third is potentially alive, yeast pellets, which could be activated with water. And then the fourth is actually alive. And the favorite one for this is Mexican jumping beans, which are actually a kind of moth larvae, which are activated by heat and really do move around, even if you're not shaking the box. So these are the 4 items, and it's very interesting to see the student debates over the difference in these 4 categories based on very limited sensory available data. I also use activities that are taken from an activity book written by Ed Prather and colleagues, and these are pen and paper exercises which you can duplicate in the classroom. In this case, there are timeline cards, 6 different eras in the history of the Earth, and then there are events in geology and biology that happen on the Earth. And they're shuffled, so there's no obvious order to them, and the students have to make the connections. They have to argue about the appropriate order, and they have to logically connect the events that happen in the history of the Earth. It's an interesting activity because students don't all do it the same way. Students working in groups will therefore come up with different answers, and then they move around the class debating and arguing with each other over whose ordering of the timeline is correct. So there's a lot of information in this activity, and when they digest it, they really do have a good understanding of the ebb and flow and the interrelationship between the biology and the planet itself. I also have other ways of doing activities. This is a good one. This is a NASA activity. The hypothetical is a spacecraft has crash landed on the moon, and the astronauts have to use a set of items available to them to get to a base a few hundred kilometers away. And they have to decide which are the most valuable items to them to survive on the moon. Here are the items, and they make a rank order of these items. You have them do it 2 ways. Individual students do it first, their own rank ordering, and then they get together in groups and do a rank ordering. And the end goal is to compare to astronauts' rankings. Those are the experts. And the differences, of course, are minimized as close as they get to the astronauts. Here is the outcome of one class doing this experiment. And it's a good and striking result. What it shows is that while the very best results come from a few individual students, sometimes who match the astronauts' rankings exactly, on average, the groups do better than the individuals. And so this activity becomes a powerful demonstration of groupthink, of why it's not a bad thing, but a good thing, and why we use group thinking and collaborative learning in classes. There's another activity that relates to the scientific method, and the hook here is UFOs or possible alien visitations. So students have to judge 3 kinds of evidence: eyewitness evidence of something strange happening in the sky that they can't explain, or photographic evidence, a classic UFO type photograph, or physical evidence, an object that doesn't seem to have a normal terrestrial origin. And they have to judge the veracity of this type of evidence and which is most reliable. And we compare the answers of ranking these. And they tend to get the right answer. They understand that eyewitness accounts are the least reliable because of the difficulty of corroboration and perception problems, that imagery is better, but it still has to be repeatable, and that physical evidence is best because it can be subject to independent analysis. And so in this activity, they learn the different types of evidence and why scientists value some types of evidence more than others. I also like to recommend students to the HAB World's capabilities. These are activities built by Ariel Ambar and his group at Arizona State University. It's a very powerful and immersive 3D environment for understanding what makes the habitability of the Earth or a planet. These are virtual field trips essentially, and they're very data rich, and they actually model, in a way, the scientific method. So this is a very effective class that's been taught for a number of years to thousands of students up at ASU, and the curricula and the pedagogy is really excellent. I've done something adventurous some while ago, and it could still be done, which is go into the 3D virtual world of Second Life and build interactive timeline of the Earth, where students create 3-dimensional virtual objects, and they can animate them too, to give a sense of some part of the history of life on Earth. And so students build little virtual exhibits essentially at different points on the timeline of the Earth, and then we all can go in as avatars and visit these exhibits So it becomes a sort of virtual museum built in a 3D world of Second Life. This is another powerful mode of pedagogy. Despite rumors to the contrary, Second Life is still alive. It had its heyday, perhaps, its peak audience maybe 2 decades ago, but it's still there doing interesting educational things. I've also, with the help of my team here at the University of Arizona, we built an astrobiology MOOC, which has now enrolled over 35,000 people. It's been around for 5 years, and over 250,000 hours of lecture videos have been watched. This MOOC is offered by Coursera, and the issue, of course, with MOOCs is that completion rates are typically quite low, below 5%. So the question we've had to wrestle with, as others do who build MOOCs, is how do you create an instructionally rich environment to engage the learners, and how do you use social media or other parts of your toolkit to engage them and let them retain the course. In other words, come back and continue with the course. Here are the demographics of the MOOC audience. This is typical for any science subject. It tends to be a sort of flat curve of age, peaking in the 20s and 30s, but a significant number of retired people. Many people in MOOCs have jobs and have higher degrees, so they're quite well educated, but they have limited time. They have families and jobs, and so they are active, interested learners, of course, lifelong learners, but they have limited time. The reach is international. Less than half of the enrolled students are in the United States. The rest are spread amongst over 170 different countries. And we've learned in this course and others that there are pieces of the curriculum and the pedagogy which increase the probability that they will complete the course. So if you can get them to stick by doing the first activity, or by being active on the discussion boards, or just even doing the first quiz and not dropping away at the first time there's something asked of them, then the probability that will increase that they complete the class. And these are high probabilities of completion with these different modes of pedagogy. Citizen science is also a useful thing to inject into a MOOC. And compared to college students, there are quite different motivations. These are lifelong learners driven by curiosity. They have a strong intrinsic motivation, whereas college students are primarily grade-driven, of course. MOOC learners are not doing the work for college credit or for a grade, so they're motivated quite differently. There are many materials out there available, and I've written a number of books on astrobiology, and one I've used in teaching is a book of interviews I did with 55 different astrobiologists. And this is very engaging material, and I get students to read them, comment on them, and make commentaries, because this tells you how science is actually done. And it's very engaging. There are the personal stories of these astrobiologists too, which really draw people in. There are other materials available on NASA websites. So NASA is very rich in its instructional materials. There are graphic novels, for example, about astrobiology. There are a large amount of curriculum materials available, open and freely available on NASA websites. There are interviews, Ask an Astrobiologist. Very many of the most famous astrobiologists you can think of are represented in the Ask an Astrobiologist series over the years. And NASA's also curated a set of videos, not of their own creation necessarily, but these are also very good tools to use in teaching methods. And then perhaps the most innovative, Eyes on Exoplanets. That's an immersive 3D environment available either on a website or as an app, which lets you pick an exoplanet system and then go in and explore the habitability, the nature of the exoplanet system, the parameters of the orbits, anything else that's known about the planets. And it's using real research data. This is very powerful, of course, and the amount of material is growing rapidly as we learn more about exoplanets. So this is a very useful thing to inject into an astrobiology course. So as you can see, there are a large number of possible tools that you can use in teaching astrobiology, especially to go beyond lecture, to engage students in interaction, in small group activities, and in immersive learning situations. So I hope you use some of these and enjoy teaching astrobiology. Thank you.
Hello everyone, I'm Sharsat Mir Sultani, astronomy educator from Iran, and today I'm here to talk with you about astronomy, language, and cultural continuity, nurturing connection for Iranian migrant youth. I want to start my talk with this beautiful image from Cassini spacecraft. In this image, we can see a part of the Saturn planet, we can see a part of the beautiful rings, and also we can see a pale blue dot, a place we call it home. When we look at the Earth, our planet, from this distance, we can feel that everyone on this planet call this pale blue dot their home. They feel that they have only one home. But if we take a closer look at this planet across different continents, different countries, we can see a huge amount of the population of the world are facing many challenges to call a place on this planet their home. And one of the results of this kind of challenges is the migration. People start to migrate from one country to another country, from one continent to another continent, and this migration can happen because of different reasons. For example, they want to have better access to education. They look for the economic opportunities. Sometimes the political issue and the war may come to into their life, and sometimes a part of the family has already migrated to another part, and the rest of the family wants to join them. When I look at this picture and when I look at my country, Iran in Middle East, which unfortunately nowadays is one of the countries with a high rates of migration, I was wondering in my mind what will happen to this civilization. Actually, for a civilization like my civilization, Iran, with a great and big background of the history, art, culture, and literature, I was thinking to myself, especially for the younger generation who has migrated to another country, what will happen to them? How are they going to stay connected with their homeland? How are they going to learn their mother tongue? How are we going to transfer our culture, our literature, our history, and everything we had inside the land to their migrated students? And also, one of the most important thing is the language, because we will see that the language is something more than a tool just to communicate with each other. How are they going to learn their mother tongue? Because in the other parts of the world, for example, they don't speak our language, Persian. So how are they going to learn that language? Actually, I started as doing astronomy education 10 years ago with the in-person classes, and one of the things I was always having in my mind were these migrated students. So one of the reasons I established the Kargah Setara project in 2017 was to reach to this student. This project is completely online based, and it has the goal to promote astronomy and space sciences for all the students, Iranian students across the globe, not only inside Iran. We started by producing educational content and publishing them on various social medias like YouTube, Instagram, Telegram, Twitter, everywhere. And then we try to use the digital platforms to have online classes, online workshops, online meetings for the Iranian students. We try to revise our methods. We try to bring STEAM and STEM activities to online classes. And we start doing astronomy education and outreach, not only for the Iran, but also at the global level. And now, as we are talking to each other, with each other, we have reached more than 10,000 students across the globe. And not only we covered all the provinces of Iran, but also we could reach to more than 50 countries across the globe. And I want to mention here that we have to remember that this revolution that we saw in online education was one of the results of the pandemic. If you remember, in 2021, suddenly across the globe, everyone were attending online classes, online meeting. A lot of digital tools came into being. A lot of digital platforms for having classes come, and that was a milestone for our project. That was when we could reach to hundreds and thousands of students inside and outside the country. This map is so interesting for me. Here you can see the time that I had only in-person classes. This is my city in Tehran, and all of my students were from this city. When online classes begin in the first semester, in less than 3 months, I remember we could cover 15 provinces in Iran, and in less than a year, we had students from all over the Iran. Imagine that in some parts of this country, the students don't have access to very high qualified education and resources, but because of online education, they could come and attend the classes. And after that phase, we covered all the provinces. We started to go to whole countries across the globe, and we could we could reach to many students from America, Canada, Australia, Africa, different countries in Europe, different countries in Asia. And today I'm going to focus on these students, the migrated students, Iranian students from different countries. I remember when I started doing online astronomy education for students inside Iran, I saw myself in a whole different era from in-person classes, and it was just like I had to revise all the methods, all the things that I knew from before. And when I started teaching migrated students, again, I felt I have to make a lot of change in my astronomy education and in the Kargah Satara project too. What was the problem? Actually, we faced a lot of challenges, and I will first tell them very shortly, and then we will go to each of them one by one. First of all, language is the most important one because we decided that our classes, even for the international students, Iranian international students, will be in Persian. But sometimes the students don't know Persian. They were born in America, for example. Most of the times, the English is their first language, and it was interesting that sometimes, for example, the student was coming from Germany, so the first language they learned was German, and then they knew English too, and then we want them to learn Persian too, so they knew two languages, and their mother tongue Persian was the third language. How are you going to teach about astronomy and space sciences to these students? Age group is very important, but when you are working at a global classes, it's not only about dividing students into secondary or primary schools. You have to divide them into very specific group, because even when you want to talk with them, you have to use different words, different methods. So age group was another a challenge we face. Also, when we were having students from different countries, the different countries had different educational system, and also they had the students from different countries, from different educational system, were coming to the classes from different backgrounds, from different level of knowledge. How could we could set a plan for all of these students? Sometimes they knew some sciences related to astronomy and space sciences at different levels, for example, mathematics, physics, and other sciences. So we had to set a course, set a lesson plan for all of them. And also, one of the most important one was the time zones, because when you are having the students from different time of the different part of the world, sometimes on the one part of the world is day and the other part is the night. So how we are going to manage this? We couldn't put all the students in one class, and then we had to revise that one too. And also, when the students are from different part of the world, the resources that we have available can differ, and we cannot just suggest one thing for all the students from all the countries. The most important one, as I mentioned before, is the language. But we have to ask, is that a limit? Is that a challenge? Is that an opportunity? The most interesting thing is that I saw that in the families, Iranian families, the most important reason they were eager to register their children in our classes, Iranian astronomy classes, was the language, because they knew that their child don't have this opportunity, for example, to go and learn Persian language directly in, for example, in another country. But they were interested in astronomy and space sciences, so they came to the class. The first language was Persian. Actually, we were having two language classes. At the same time, we were talking both English and Persian, but the main focus was on Persian. So they had the chance to, not directly, but they could learn Persian language. And when you learn language, you can read books, you can go to the literature, you can go to read your history, learn about your culture. And for teaching Persian language to these students, we use different methods. We use game-based learning, we use storytelling, we use puppet show. We'll see later. And even we started teaching Persian alphabet to the students who has never seen the Persian alphabet before. With what? With astronomical objects. For example, they were interested in stars and planets. We call them, okay, in Persian, we call planet sayyare. Sayyare, okay? The first alphabet is having this sound, se, like S, okay? This alphabet in Persian is se, sin, and it has a sound like the S. Okay, I could teach the students. Here we have the planets. We call it in Persian, sayyare. And then from here, I could teach them sin, se. Or another example, in Persian, we call a star, sethare. We could teach them another time this alphabet again. And we use different methods to teach them Persian. And here you can see
ولی یه چیزی میخواد بگی این والی بچه ها هی مر داریم بالا پایین میپره. آره بچه ها من یه چیزی رو میخواستم بگم. این نکته ای رو بهتره که در نظر بگیرید. من سعی میکنم به شما امروز چیزای خوبی راجع به همکارای خودم، فضاپیماها و ربات ها یاد بدم. So today I'm going to teach you about the rovers and the spacecraft and the space mission in the Mars, and I'm going to give you very great information. Okay, we have three types of.
And consider this point. These students from different part of the world. Now they had the chance to meet their friends from different part of the world, Iranian people, which may not be possible in their country. We said that age matters. Age, one of the most important things in online global astronomy education. We had to adopt the language, because when you are talking to a 5-year-old child and you're going to use some words and the level of literature, you have to adopt that. When you are adopting the language you are using and the level of the language you are using, you have to pay attention to your methods. So again, we had to revise all the methods that we had to teach astronomy to these students too. And different countries, we could see that Europe has some specific educational system. America, for example, has some educational systems, and these students were from similar time zones where they coming to class. They were having similar time zones, but different background and different educational system. It could make the lessons for us a little bit challenging. So we had to set a lesson plan that fits everyone. And this one was very complicated, but that was one of the challenges we had to handle. And another interesting thing that we faced was the different time zones. And when we had different time zones, we were not thinking about the students. This time we were thinking about the teachers. We saw how important is that to train more teachers for our project, because you cannot ask a teacher, okay, stay awake whole night and teach the students, and beginning from the morning you are going to teach to the 50 countries from different time zones. That was showing us the importance of teacher training and having multiple teachers. So then we could divide the students, the class at different time zones, to different teachers, so they could be present in their classes with so much energy and smile on their face actually. So that was another challenges we could handle actually. And then we strongly believe in doing hands-on science activities, but because the resources and the materials we have available in different parts of the world, different families with different backgrounds, is completely different from each other, we find a solution for this one too. And we ask the students, do the activities with all the things that you have available at home. We didn't encourage them to buy anything. We didn't tell them you have to bring this specific thing, which actually made them more creative, which actually improved their imagination. So that was one of the challenges and the solution we could find for one of the challenges we faced in the astronomy education for the students out of Iran. So in conclusion, I can say that astronomy education can play significant role in education and also educating the students who has migrated to another country. We can transfer indigenous knowledge to them. And also it's amazing that in every nation, in every language, astronomy education, I think I had this potentiality to be served as a tool for teaching language, teaching alphabet to the students, as I mentioned before. And also through online astronomy education, you can transfer culture, heritage, literature, anything related to the homeland of the students who are living far from their land. You can transfer that, and somehow you can keep these roots into their homeland safe, and they always, no matter wherever they are living, they can feel this strong connection to their homeland. So thanks for your attention.